I'm Margaret Preston, president of Power Over Parkinson's, and today, in conjunction with our Pop Profile series, we have Dr. Jamie Eberling with us. Dr. Eberling received her PhD from the University of California at Berkeley and earned her postdoctoral training in PET imaging at the Lawrence Berkeley National Laboratory. At the Michael J. Fox Foundation, Dr. Eberling has been involved in a number of different programs over the years. Most notably, Dr. Eberling has overseen the PET imaging program since 2009 and launched the foundation's dedicated effort to develop a selective alpha-synuclein PET tracer in 2010. In 2016, Dr. Eberling announced a $2 million prize to the first group to develop a selective alpha-synuclein PET tracer. And today, her focus continues to be on the development of novel PET tracers for a variety of different pathological and therapeutical targets. Dr. Eberling is the Senior Vice President and Head of Imaging at the Michael J. Fox Foundation. Dr. Eberling, thank you so much for being with us today.
Oh, thank you for inviting me. My pleasure.
Absolutely. Well, let's jump right in and kind of start with the basics if we can. Share with our listeners what alpha-synuclein is and what role does it play in Parkinson's disease?
Sure. So alpha-synuclein is a protein that's found in everybody and throughout the body, actually, including in the brain. In Parkinson's disease, it becomes misfolded. So the structure of the protein changes and it forms clumps in the brain. And the clumps are contained in what we call Lewy bodies, which many of your listeners may be aware of. And we know that Lewy bodies are found in the brains of Parkinson's patients at autopsy. So at autopsy, if you look in the brain, there are Lewy bodies which contain alpha-synuclein throughout the brain. So we know that that it is involved in the disease. It's sort of the pathological signature of the disease. But we have no way of seeing it in the brain or knowing how much of it is in the brain and where it is right now. You have to wait till autopsy. So what we'd like to do is to be able to image the synuclein in the brain using PET imaging so we can see where it is, how much is there, and how does the accumulation of the protein in different areas of the brain, what does that tell us about the symptoms we see in patients? We think that depending on where the pathology is, you may see different symptoms in patients. So if people have a lot of pathology in the cerebral cortex, you may see more cognitive issues than in subjects who don't have pathology in the cerebral cortex. And we know that as the disease progresses, the pathology sort of spreads throughout the brain. In some subjects, it reaches, the cortex, it's all over the place. In others, it doesn't spread as much. We don't understand why. And the other thing we don't understand is in some subjects, it seems to progress quite quickly. In others, it may progress quite slowly. And we think that has to do with the spread of the pathology in the brain. So we've been working, as you mentioned, since I got here over about 17 years ago to develop an alpha-synuclein PET tracer. And this would enable us to see the alpha-synuclein in the brain using a PET scan. And we can do something similar to this in Alzheimer's disease, where you can actually image the pathological proteins. There's two of them in Alzheimer's disease, amyloid and tau. And we have PET tracers for both of those so that we can actually image amyloid in the brain and tau in the brain. Amyloid was the first protein that we were able to image in the brain. And that began, I think it was the first scans were done in the early 2000s. And then tau came along around 2013 were the first human images of tau in the brain. So it took a long time.
Yeah.
And we've been working on this for a long time. We think we're getting close to having a tracer for alpha-synuclein that can be used clinically in patients, that could be used either to diagnose the disease, to follow the progression of the disease. So if you scan somebody early on and then you scan them later, you could see how the pathology spreads in the disease and what that means in terms of how the symptoms change. Mm-hmm. But very importantly, we think that it could be used in clinical trials that are testing treatments that are aimed at either slowing or stopping the progression of the disease or ultimately at preventing the disease. Yeah. And many of the treatments are aimed at reducing the alpha-synuclein in the disease or or reducing its spread. So we need a way to see if the drugs are working.
Sure.
And right now, we don't have a way of measuring the synuclein in a way that would tell us, yes, the drug is doing what we think it's doing and it's effective or it's not effective. So for therapeutic development, it's really a critical tool that we need.
Absolutely. Well, share. I know a lot of our listeners have most likely heard of DAT scan or potentially have gone through one at point of diagnosis, but share with our listeners the difference between the DAT scan and the PET scan that's currently really at the center, as you discussed, of Parkinson's research.
Yeah, so DAT scan measures dopamine function in the brain, which is also critical in Parkinson's disease. We know that dopamine function declines as the disease progresses, and probably when patients are diagnosed with the disease, it's already quite compromised. So if you look at dopamine function using DAT scan, you can see that if you look at a person without Parkinson's disease versus a person with Parkinson's disease, the person without Parkinson's disease, you see the striatum light up. So you see these two comma-like lighted up places in the brain. In somebody with Parkinson's disease, it's much dimmer, and eventually you don't see much at all. So it gives us a way of measuring sort of what functionally changes in the disease. What we think happens is that the alpha-synuclein accumulates in the dopamine-producing cells and causes them not to function well anymore, and eventually the cells start to die. So the alpha-synuclein is the pathology, and what it affects is the dopamine function. But so the dopamine imaging is very useful in Parkinson's disease. It helps us with diagnosis. It's not specific for Parkinson's disease. So other diseases like multiple system atrophy, MSA, and progressive supranuclear palsy, PSP, both have compromised dopamine function. They have some different symptoms, and the progression is different. So there are things that distinguish them. But if you look at the brain scan, that just shows that dopamine function is affected. Whereas with something like alpha-synuclein, it's much more specific for Parkinson's disease, and it's also directly related to what the therapeutic is targeting. They're targeting the pathology. So drug companies like to have the most direct measure as possible to tell them if their drug is working. So dopamine imaging can help. Maybe if you image somebody early on and they show some reduction in dopamine function, and then you treat them and it doesn't change over time, that's useful to know. It suggests the drug is working. But the drug companies are much more comfortable if they have a direct measure of what they're trying to alter.
That makes sense. Thank you for that explanation. Well, with recent advancements, how has PET imaging in Parkinson's really evolved as it relates to viewing the alpha-synuclein in living patients? I know we talked about during autopsy, but now we have the ability to kind of utilize this test in living patients. So talk to us through that evolution.
Yeah. So over the years, there have been a few PET tracers, alpha-synuclein PET tracers, tested in humans. To date, they have not worked all that well. And we think it's because the chemistry just needs to be tweaked a little more. It's difficult to develop. These are essentially radio-labeled drugs. And it's difficult to develop a drug that binds to only one thing and nothing else. So that's why drugs have side effects, because they almost always bind to something other than what you want it to bind to. You just have to minimize the side effects. With PET imaging, whatever it binds to is seen in the image, and you don't know if it's synuclein or something else that it's binding to. So that's been very challenging to find drugs that bind just to alpha-synuclein and not other things. So the drugs that have been, or the tracers that have been tested to date, bind to different stuff, and they just haven't been optimal for imaging synuclein. Right now, we are funding 3 groups to test new alpha-synuclein PET tracers in humans. There are others that are being tested in humans that we're not funding. To date, there have been probably 10 that have been tested in humans, but the ones that we're looking at now look much better, look really promising. And we think that we need to get some more data before we'll know for sure how good they are. But we think this year we'll have a really good idea, at least for those 3 I just mentioned. And the next step would be to just keep getting more data in more subjects and then to look in different types of diseases also, because we know that there's alpha-synuclein in Alzheimer's disease. So it'd be interesting to know like what role it plays there. But the first step is to find a tracer.
Absolutely.
I think we're getting really close.
That's
the
exciting.
other thing that I think will help us is there's a new PET scanner that's been developed. It's the highest resolution PET scanner in the world.
Okay.
Which means that with that PET scanner, you can see very small brain structures. With current technology, you can kind of see some blurry looking structures, but it's hard to say, is that the
Whether it is or
Niagara? It's like, exactly what is it?
Sure.
So with this new PET camera, you can clearly make out small brain structures like the substantia nigra, which is where those dopamine cells live and die. So we really need to be able to see that on a PET scan. It's very sensitive. So it means that even if there are low levels of pathology, you should be able to detect them with this PET scanner technology. Whereas with the current technology, you may not be able to.
Okay.
So I think the advancements in chemistry, which allow us to make steps in progress in the tracer, and the advancement in PET technology, which enables us to make improvements in the actual scanner, together, those could be the game changer.
Okay, that makes sense, and kind of outlines the evolution, how far we've come, and with those two components, and really, like you said, becoming the game changer in the long run.
Yes.
Talk to us about the ability to see alpha-synuclein in real time in living patients, of course. What can be discovered? We think about diagnostics, therapeutics. Here, talk to us about some of the goals, those goals we all dream about that can be discovered as a result of this.
Yes. So let's say that one of the scanners or one of the tracers that I talked about ends up being the winner. Now we've got a PET tracer. What are we going to do with it? One, we can use it for potentially for diagnosis. So we think that you should be able to see synuclein on a PET scan pretty early, at a time where diagnosis may be less certain. And even dopamine imaging may not help us when it's very early, because as I mentioned, there's these other diseases that show dopamine dysfunction. And early on, it's hard to distinguish them. The synuclein may help us with that. And in PPMI, our big biomarker study, we are getting subjects who are at risk for Parkinson's disease. And so they may develop it later. They don't have symptoms yet, but maybe we can see something on the PET scan very early. And hopefully where we're going is prevention ultimately.
Yes.
So you want to be able to catch this as early as possible.
Yeah.
The other thing is in selecting subjects for clinical trials, if it's a Parkinson's trial, you want to be sure that those subjects have synuclein in their brain. If you're trying to use a synuclein lowering therapeutic, if they don't have synuclein in their brain, like it's just going to make it more difficult to get a signal in a clinical trial. And we saw this in the Alzheimer's field before they used amyloid imaging to select patients. They discovered when they went back and looked at previous clinical trials that not all those subjects even had amyloid in their brains.
Interesting.
So the trials failed, but is it because the drug didn't work or because they didn't have the right patients? So that's another very important use. I mentioned before that just making sure that the drug is working. So you look at synuclein before treatment, you look after, and you see is the synuclein being lowered or is it at least not increasing over time?
Right.
So super important for drug development. And then also just for tracking the disease over time. So looking at the progression of the disease and how that relates to different symptoms. And depending on where you see the synuclein in the brain, it could lead to different treatments. There could be treatments that help with cognitive function. And if you know there's synuclein in the cortex and they're having problem with cognition, maybe you want to treat that as well as motor symptoms. It could lead to combination therapies. But we think just having biomarkers like the PET scan and other biomarkers too, things you can measure in the blood or cerebrospinal fluid, will help us to really precisely treat individual patients. So that because we know the disease is different in everybody, that's why the symptoms are different, the progression looks different. Well, they should probably be treated different too.
Yeah, absolutely.
But unless you really understand the underlying biology using biomarkers, you can't do that.
Right. I think about, you've outlined so many benefits in the long term of this. And I think about how many folks have these fuzzy diagnosis stories, right? 5, 10 years, potentially being symptomatic, maybe getting misdiagnosed or undiagnosed. So I just think about that component alone in terms of refinement through this research is very exciting.
Yes, I definitely think that's true. I also should mention that ultimately we would like to be able to just do a blood test. You go and you get your bloods done when at your annual physical, and they can look in the blood and say, look, there's synuclein. This person is at risk for Parkinson's disease. We should treat them. That's ultimately what we want. But and there's many blood tests and there's cerebral spinal fluid tests. There are different things being developed, but you really need the PET scan in order to validate those other tests.
Okay.
So we can say that, oh, we're measuring synuclein in the blood. It must mean that it's in the brain somewhere. But unless you can see in the brain and then measure in the blood and correlate the two, it's just an assumption.
It's still shot in the dark. Yeah. Okay.
Yeah. So ultimately, we would like to be able to do a blood test, but the PET scanning is necessary in order to validate whatever other type of biomarker that you're developing.
Okay. Well, we talked a little bit about the amyloid and the tau, but why has finding the alpha-synuclein PET tracers been a little bit of a harder task than the amyloid and tau protein?
Yes. The biggest difference is amyloid, there's tons of it in the brains of Alzheimer's patients. It's all over the place, and they're big clumps of protein.
Okay.
So it's just more of it, and it's bigger clumps, easier to see. It's like if you take a picture of something really small, it's going to be hard to see and blurry on the picture. Whereas if you have a better camera, you're going to be able to pick up things that you wouldn't be able to.
That makes sense.
So it was an easier task for amyloid. That's why that was the first one developed. Okay. Tau is kind of in the middle between synuclein and amyloid. There's less than amyloid. There's probably more than alpha-synuclein. So it's a little bit easier, but it's pretty challenging as well. And now there are several very good tau PET tracers out there that are being used. So that gives us great hope.
Yes, absolutely.
With the most recent advances in the chemistry, it's looking very promising. I mean, there was a while there where people were thinking maybe it just can't be done.
Yeah.
But I think now we're feeling pretty confident that not only can it be done, but we will know in the next months to a year.
Yeah.
So very
perseverance.
It's not easy. I'm not a patient.
I don't doubt that. As someone on the outside, kind of doing the groundwork with a little less complexity, we can't thank you enough for the perseverance, because you're right. You could have probably said, like, this is hard. It's real small. We can't capture it. But we thank you for that perseverance.
I mean, I think that at the Fox Foundation, we understand how important this is for drug development for the patients. I mean, we need this. We can't give up. We cannot afford to give up. So that's, I mean, I said at times, like, I'm thinking maybe we should just give up. I would never give up.
Yeah.
And I'm really glad that I never did, because I think very close. So I mean, that's what motivates us every day in our jobs, is that patients need this. So we can't let them down.
Absolutely. Thank you. We talked about individualized treatment plans. So if we are better able to see and understand, of course, the alpha-synuclein dopamine through this imaging, it sounds like we can probably start refining treatment, improve diagnostics, and create this individualized treatment plan, based on disease pathology. I think we touched on it. Can you elaborate on that a little bit more?
Yeah, I mean, I think we're still very early stages for that. Hopefully we'll get this alpha-synuclein PET tracer, and then the companies that are developing therapies that target alpha-synuclein can enroll the right subjects in their trials, and it will be, I mean, I think in the beginning it won't be, it'll basically be if you have alpha-synuclein and Parkinson's disease, you would be included in the trial. There's other exclusion things, but it wouldn't be really precision medicine at that point. The way I think about it, the way I think about it is you measure multiple things and then you kind of tailor the treatment based on multiple different biomarkers, or so that you really understand what that person's individual biology looks like. And that will take more than just dopamine and alpha-synuclein. I think we'll need other biomarkers, which we're working on.
Yeah.
So it's getting to that point for Alzheimer's disease, where now they're starting to target both amyloid and tau in the same patients. And in some patients, it makes more sense just to look at amyloid. In others, you need tau and amyloid. In others, it may just be tau. So they've got more biomarkers to utilize than we do at this point, but that's the direction we're headed in.
I was going to say, but seeing that groundwork laid is probably very promising in this space as well. And of course, for patients, like we talked about, having that individualized plan is so important, because we all know how different it is from person to person. So it's definitely an exciting concept to have things a little bit more tailored, with less like, let's try this like trying and failing medications, and having kind of a more personalized plan.
And hopefully, rather than just measuring the symptoms, you're measuring these biomarkers that tell you what is happening with the underlying biology.
Absolutely. Thank you for that explanation. Well, as we wrap up, what can those living with Parkinson's disease, or how can they learn a little bit more about this research? How can they become involved related to this brain imaging research and the Fox Foundation?
Well, we certainly have information available on our website about the synuclein program. We've been doing this for a long time, so we definitely have information there. But as I mentioned, once one of these tracers, once we feel that it's looking pretty good, it will be included in the PPMI study. So subjects that are already in the PPMI study would, depending on where they are located, initially it might be limited in terms of geography, and then it will be more widely available as time progresses. But there would be an opportunity to volunteer, to be in the study, to collect more data with these new tracers in PPMI. So PPMI is always a great, we get so much information, especially regarding biomarkers, from the PPMI study. It's really been a game changer for the field. So, I mean, that's sort of my best suggestion for how to help individually. But certainly there's a lot of information available on our website. And as we get more information about these new tracers that are looking promising, I'm sure we'll have webinars, and we'll have more documents available that people can read about it and learn more about it. But well, we will not be quiet about it, I can tell you.
As you shouldn't. Yeah. Well, thank you. I mean, the excitement is palpable, coming from the Fox Foundation down to individual localities such as here in Central Virginia. So we can't thank you enough for sharing your time with us for the series, for your perseverance, for your work in this space. And we'll link everything over so folks can sign up for the Fox Foundation newsletter and get involved in ways that's suitable for them. So Dr. Eberling, I can't thank you guys enough for everything you're doing over there as it relates to imaging and researching as a whole, and sharing your time with this series.
Yeah, it's my pleasure. And I hope that I can come back sometime and tell you about a validated alpha-synuclein PET tracer, because that will be a very exciting day. And you probably won't be able to shut me up.
Well, you're on the hook now. So I don't even have to ask. I heard a yes.
You've got a yes, for sure.
Absolutely. Well, thank you so much.
Okay, thank you for having me. Appreciate it.
Yep.
Okay, bye.